thank you guys for having me, letting me talk about standard model effective field theory fits using our tool called SFitter, and more specific, what you're interested in, how we use pyhf to help us in all of this, and what we can do with it. So just very quickly, to quickly set the stage, what we do is global SMEFT analyses using this SFitter framework to put constraints on the beyond the standard model physics. Then I'm going to talk about what SFitter itself actually is, because you need to understand what we do with the data to understand what we can use pyhf for to improve our analysis in the end, which is why the second part then goes into more detail on what pyhf does, what we use the likelihoods for, and what kind of improvements we gain from using these likelihoods, and what more we could possibly try to do in the future. So starting very quickly with the introduction of the standard model effective field theory, as I said, I assume most people here already know at least the basics of it, that we take the Lagrangian of the standard model, assume that any kind of new physics only take place at a larger physics scale, which we call lambda, and then we extend this Lagrangian by adding higher order operators to this Lagrangian, suppressed by these corresponding orders of the new physics scale. These are then parameterized by these Wilson coefficients C, and using these, we can then compute the effect those have on our observables that we use in the fit. For our effective field theory fits in SFitter, we always compute contributions up to quadratic orders in the fit. So as you can see, there's here linear orders, quadratic orders. Obviously, to this order, one can also expect dimension 8 operators to include to have contributions. But for all of the data we look at, we expect these contributions to be small. So for this analysis, we completely stick to dimension 6 operators, which is the norm for most fits up to today anyway. Now to quickly introduce what kind of data we used and are looking at. Currently, all of the results I'm going to show you are basically based on a paper we did for a global SMEFT analysis in the top sector published back in 2019. And that's basically include data from TT bar, TTC, TTW, and single top production, both differential and total cross sections, to have, well, a global SMEFT analysis. In total, there's approximately 116 data points, which then we use to constrain all of those 22 different dimension 6 operators you can see on the right side. To get to those, we had to, or we did add an additional flavor symmetry between the lighter and heavier quark flavors, as you can see there, to just simply restrict our space of Wilson coefficients to a reasonable amount later. So the details of this whole data set are not too important for what I'm going to discuss now, but all of the results I'm going to show you basically plot-wise will be based on the fit to this data on the top sector. So now we can actually continue by talking about what SFitter is and how we actually perform this fit. So first of all, I'm just going to give a quick rundown of what we usually tell people to sell what SFitter does. So like I said, it was used for different SMEFT analyses previously. I just explained the top analysis, but it was also used for Higgs, boson and electroweak precision data. And what we basically pride ourselves in is the comprehensive treatment of uncertainties and full correlation between systematic uncertainties within the same experiments. Also, we have two different ways of statistical analysis, allowing for both profiling and marginalization approaches. And in the end, we also use Monte Carlo Markov chains to map out the likelihoods. So with this, I have a list of different things I basically try to talk to you about. But the point of this first part is getting into detail, what exactly do I mean by this? So starting with the exclusive likelihood. So for all of these statistical analyses, we naturally need to construct a likelihood. And so as you can see, the exclusive likelihood we work with is simply like the product of the Poisson giving the probability of the measured data matching our prediction with the model parameters alpha, which are going to be the Wilson coefficients of our standard model effective field theory, these nuisance parameters theta, which are going to be the uncertainties we're going to look at later, and then also obviously this going to depend on a background measurement B, which is then also why the second term comes in, where we need to take into account that the background was measured in some kind of control region and then extrapolated into the region of interest. And then finally, the last parts are some additional constraint terms on the different nuisance parameters we include in the fit. And those actually then depend on the kind of uncertainty we consider. And the uncertainties we look at in our SFitter fits are systematic, statistical, and theoretical. So for systematic uncertainties, we assume them to be Gaussian because, like, for example, with the luminosity, we would expect those to come from some kind of secondary measurement. So with the large amount of data measured there, we would expect those to be Gaussian. So we assume most of the systematics to be Gaussian. Statistical uncertainties, we simply take as a Poisson distribution. And for theory uncertainties, we actually assume them to be flat, because we do not expect any particular value in the uncertainty ranges of theory uncertainties to be more likely than any other. Because if one cannot simply say one computes this uncertainty over and over again, and one has a certain value where you would expect to end up in the end. In the end, these usually come from something like scale uncertainties and stuff like this. So you know the ranges they're in, but no particular value is expected to be any more likely than another. Naturally, those are still just assumptions for now. So I'm going to come back to this a bit later when talking about the more details. Yes, with this, I talked about uncertainties, but obviously we want to look at more than just a single measurement. Like I said, it's a global fit. We're going to look at a lot of different measurements. So we need to generalize to more than a single measurement. The expression for the likelihood is simple. One just simply takes the product over different channels and now needs to take into account all of the different processes. And the interesting part now comes in, once again, in the constraint terms in the end, because using those constraint terms, we can now also actually introduce these additional correlations between the systematic uncertainties I talked about earlier. So basically, in this, we can then use these constraints to fully correlate all kind of systematic uncertainties between these measurements. And what I mean by these systematic uncertainties, I here on the right just have a quick list of our previous analysis, different kind of systematic uncertainties we have. So basically, we assign different uncertainties we get from paper to these categories, and every systematic uncertainty for all of these different measurements within AppList is then correlated to the same uncertainty from a different measurement within AppList completely. And the same goes for all of the CMS measurements we add. The only exceptions is the luminosity, which is correlated between both AppList CMS and all measurements, because obviously all of the measurements are taken at the LHC. So this is a reasonable assumption for us. And why do we think we care, and why is this important to us? Because of this, to show this, I have a plot from one of our previous paper. So this is a fit not in the top sector, but with the Higgs electroweak precision and diboson data. But basically here in orange, you see the results if you neglect any of these correlations, and in blue, if you take all of them into account. So you can see a very clear shift in the results just after including all of these correlations between these uncertainties. Yeah, which is why these correlations and uncertainties are so important to us in our fits. Continuing quickly with profiling marginalization. So basically, we have our likelihood, as I've shown you just now, but obviously all of these nuisance parameters, as the name suggests, are not too interesting to us physically. So now we can actually decide what are we going to do with them. Are we either going to profile, so basically put the nuisance parameters to the values that maximize the likelihood, or marginalize over them, so integrate them out in the end. Why do we care about this? Once again, I'm going to show a plot from one of our previous papers, where basically here, just as an example, on the left, we have a comparison of the product of a Gaussian and one uniform distribution. So basically one systematic and one theory uncertainty, basically in our case, and show that in blue, we have the result from marginalization, and in green, we have the profiled results. So one can clearly see that the flat behavior of the flat uncertainties, one can still see very clearly after profiling, while even with even with just a single theory uncertainty, the blue marginalized results become much closer to the Gaussian. We can also see here in orange. On the right, we have the exact same thing this time, but with 3 different theory uncertainties. So basically just adding more theory uncertainties. And once again, technically, there's also an orange Gaussian curve on the right plot, but you can see that the marginalized results now basically agree with those with the Gaussian results, while the profiled results still have this very flat distribution. This is, for now, this was just to show how this would work. So to show some results from one of our actual fits. So basically, for now here, just the constraints, the 68%, 95% constraints on the different Wilson coefficients I showed you at the beginning. So basically in orange, you have the constraints you get from the profiled result, and in blue, the constraints from the marginalized results. And already just by looking at all of these constraints, one can see that the constraints coming from this marginalized results are tighter than those from the profiling. And this can now already be kind of understood, thinking back to the plots I showed just now, and also when just looking at the one-dimensional likelihood plots here. So especially in the plot here in the middle, what can I already see? The profiled results here in orange have this flat region I've shown you before, while the marginalized results become much more Gaussian for all of these. So basically, we see that these our flat theory uncertainties lead to different results when we perform either profiling or marginalization. So yes, with this, I showed basically quickly what SFitter is, and here just a quick slide to talk about what you should take away from this. The uncertainty treatment, both systematic and theoretical, is very important, as I've just shown you. And theory predictions and theory uncertainties we can do ourselves. We compute these, and this is okay. But systematic uncertainties are provided by by experiment. So now we get to how these results are provided, how we can use them. So now we can talk about actually using pyhf to implement data into our framework in the end. Starting again, I assume the slide I don't need to explain too much. This has the likelihoods that are published in the SFitter format give us all the different values we need and a large number of different nuisance parameters in the end. So using pyhf and cabinetry, we can now try to analyze these likelihoods and the nuisance parameters and see how we can implement these into our final analysis. For the results I'm going to show you, I have 2 different likelihoods I looked at. One was the measurement for the TT bar total cross-section, and the other one I looked at the total cross-section of the TTZ measurement. So basically, just using pyhf, one can obviously, people know, just reproduce results for different nuisance parameters very easily. One can find the impact and the different pools of individual nuisance parameters nicely and get results provided in different papers very quickly and easily. But the problem is, or not the problem, but there's hundreds of different nuisance parameters in the final likelihoods provided. And I showed you before that the systematic uncertainties we consider in our fit is an order of 10 to 20 at most, maybe. So obviously we cannot for now, we cannot just implement every single nuisance parameter, especially once you have more and more measurements, this would be unreasonable. So to see what we do with this, I'm going to talk about a bit on how we previously worked with these uncertainties and how we implemented them. So basically here on the very right is a table of different systematic uncertainties provided directly in the paper. So the values on the right, I just took directly from the paper, just a table like this. And usually we use these uncertainties and put them into the SFitter framework. But now using pyhf and the full likelihood, we can actually compute these uncertainties ourselves for these different groups by performing this profile likelihood fits. And for that, I also have just a quick list of the different results for the reproduced values using pyhf. So obviously they agree, which is what we'd expect, but it's a nice quick check to make sure it's fine. But using this, we could now also just simply in the exact same way put these uncertainties as they are into our framework again. Problem is, like, we couldn't just use these likelihoods as is, put them into our framework, have them compute these uncertainties, because like automation is difficult, because we would need to assign all of these different nuisance parameters to the correct categories, and the naming conventions are definitely inconsistent. For some of the different systematics, it would be fine, but others would probably be very difficult to actually include in the end. But going more into why this is useful to us, like I said, these uncertainties we got in the table, we usually simply put in these systematic uncertainty categories within our SFitter tool. So with some of them, it's easy. For example, like B tagging can go into B tagging. That's simple enough. Pileup is the same, but at some point you see that, for example, you have jets and the transverse missing transverse energy. And in our SFitter fit, these are technically separated now. So since we have a global analysis and this many different kinds of measurements, we basically would have to either decide what to do with this one now, put it into one of the categories, split it up maybe. In the end, we correlate these. So in the end, this could lead to some inconsistent correlations between these different uncertainties. Or we can now actually use the likelihood we are provided, because since we have now control basically over almost all of the different nuisance parameters, it's easy to actually split this up now the way we want them to, without having to adjust any of our previous measurements, and can actually just simply compute the uncertainties coming from the jets and the missing transverse energies separately to make sure that we don't have any mixing between the systematic uncertainties that we couldn't avoid previously, because if we're just giving this table and we cannot really do anything, and at some point it's possible that we're adding more and more measurements, there's going to be more conflicting information, which would just make it much more difficult and less useful to correlate our systematics in the end. Continuing, just very quickly, this was just a low-dimensional fit to only a single operator CTG, which is mostly affected by these total rate measurements, to make sure that if we use our likelihoods using pyhf and implement everything using this, we get the same results, which is exactly what we would like to see. So this is just a quick quick way to show that at least reproducing what we already can do is already much easier. Continuing, looking at nuisance parameters and parameter scans. So as I said, we now can look at all of the individual nuisance parameters. So I showed here an example, once again, from the likelihood for the TT bar measurement. And on the left, I just chose one of those nuisance parameters, which when you compare it to the Gaussian approximation, is very Gaussian. And on the right, I picked the one nuisance parameter that actually is the most non-Gaussian result from all of these parameters. So why do I care about this? Because as I said in the beginning, within our framework, we assume all of our systematic uncertainties to be Gaussian. So when we look at the nuisance parameter on the left, we can already see this would be quite a reasonable assumption. But when looking at the one on the right, it's already decently well described by a Gaussian, but not quite not perfectly. But in the end, like I said, we put these into these uncertainty categories. So this is maybe 5 out of all of the 100-something nuisance parameters show this non-Gaussian behavior. So after combining all of these, this non-Gaussian behavior is washed out, and in the end, we have very systematic, very Gaussian-like systematic uncertainties. So this is a nice way for us to verify that our Gaussian systematic assumption is reasonable. Continuing with assumptions we've made within our fit. Previously, or let's say, now that we have this profile of likelihood fit, after every fit, we can also get the correlations between the different nuisance parameters within this likelihood. So when we just perform this fit and look at some of the few nuisance parameters here, I just showed you basically the strongest, those with the strongest correlations. We see that there's already quite a few that are actually quite strongly correlated. And within our fit, there's absolutely no correlations between the systematics I've showed you. But just looking at this one, could expect maybe there's actual correlations between these we need to implement. This is now, once again, where we basically go and have to put these nuisance parameters first into the different categories. And one can then, once again, just compute the different correlations. And on the right is basically the correlations between the systematics we then finally implement into our fit. And basically one can easily see almost all correlations between those basically vanish, because the strongly correlated parameters are obviously in the same kind of group in the end. So the strong correlations disappear within those. So this is once again basically a nice way for us to confirm that the way we've set up things in the past, the way we chose the different systematic uncertainties, it was a reasonable assumption that they are then fully uncorrelated. this is an example for just one of these likelihoods. We also check this for multiple different ones, and basically for all of them, it happens that there's a few nuisance parameters that are strongly correlated, but in the final groups we use in the end, we basically find no correlation at all. With at most very, very small correlations, we still neglect in the end. Okay, in the end, we are doing a standard model effective field theory fit. So what we care about at the very end is the constraints. So this here is basically, once again, just a low dimensional fit to see what kind of effect adding these new measurements to our old data set would have on the constraints. Looking at these, the orange curve is after we implemented these new results, we see that there's only a very small shift in the whole result, and the constraints themselves do not really get any tighter. This is not too unexpected since, as I said, we only added total rate measurements. Those are basically already very well constrained. And using these pyhf likelihoods, we basically just had a different way of implementing uncertainties, but this we would not expect these constraints to change too much. But as I said, the main reason behind this is that this is a total rate measurement. So it would probably, or it will be much more interesting if we were able to actually get more likelihoods for differential distributions that are SMEFT sensitive. So to quickly come to a conclusion, summarizing first, to our SFitter framework, what we care about really is the correlations, is the uncertainties, their correlations, both theoretical, systematic. Obviously, what I'm here talking about here with pyhf is mostly the systematics. Like I was able to show that using it for now, we were able to basically just show that what we did before was nice, and possibly in the future, if we have more likelihoods available, because currently only some very select few we would be able to implement into our framework in the end. We could also try to adapt the systematic uncertainties we use and everything else much more nicely using these likelihoods. However, as I've shown you, the current likelihoods we use are not particularly SMEFT sensitive. So what we would love to have is to have a likelihood for a really nice measurement, very like useful for SMEFT studies with high kinematic regimes and stuff like this, because this would allow for different ways of also, if we have a differential distribution, extracting systematic uncertainties using the full likelihood would also be much more interesting than just having to, once again, have some weird assumption we would need to do to properly do those. And also, we would love to check if actually implementing some standard model effective field theory effects in the published likelihood itself already before computing all of these uncertainties would have some kind of interesting effect on this. But for now, since all of the data we have was not too sensitive, we have not done so yet. But yes, that's it.
Nice. Yeah, thanks very much for this nice talk. Let's go again to Zoom first to see if there's any questions. Okay, so I don't see any right now, so maybe we can go to the room. Karsten?
Yeah, thanks a lot. This is thanks a lot for this talk. This was really nice to see. Actually, so this is very close to my heart because I'm a EFT person in Atlas, and I work on these global EFT combinations and Higgs EFT combinations. And seeing what you do with this is really amazing because this, to me, this talk is the reason why we publish likelihoods, right? So thanks for thanks for doing this. I do have a few very detailed questions, which is specifically, so you mentioned that you don't want to correlate the nuisance parameters on the individual parameter level, but you put them in these groups and then you correlate these groups. Now, what we do in Atlas, at least in these combinations, is that we do actually correlate them on the single parameter level. So what is your rationale for why you want to not do that?
At the moment, really just the fact that if we have to, at some point would be too many, basically.
So this is a software limitation?
Yeah, for now, yes.
Okay, so this is, so basically, so what is actually the backend that you use in SFitter to do the minimization in the end?
Okay. Wait.
It's fine, we can also take this offline. I'm just curious for why it doesn't work for you, because this is basically the bread and butter of what we do. So I'm wondering why you decided to not do this. Then you mentioned that you specifically select what constraint terms to use. Now, since you do have the likelihoods available, you in principle also have the constraint terms that have been used by the experiments, right? Yeah. So what is your rationale for not using those and instead coming up with your own?
Basically, for now, we didn't have them until now. So this is basically the first step to show we can do this.
Okay. Nice.
And then like it's always further and further do more. But yeah, it's true. We can technically also look at those and directly implement them. I don't think I see a reason why we wouldn't be able to.
Okay. Okay, yeah, that's cool. Thanks. And then maybe one last thing, because so in these big atlas like Higgs or EFT combinations, we typically also do these rotations of the basis in order to make sure that the resulting Wilson coefficients that we fit are actually reasonably diagonal, let's say. So did you, or do you also do something like this where you rotate your basis in order to improve your extraction efficiency? Or did you do something like a closure study where you try to back rotate one of our results and see what happens?
I personally am not too aware of doing any of this. I only have been working on this for like at most half a year, so sorry if I'm not too
yeah, no worries, I'll go
the details yet. But from what I personally know, I don't think so. I hope. But
okay, because to me this would be like the most interesting part, to see whether sort of this method that we use to sort of improve the extraction efficiency of the information from the likelihoods is something that is like on the side of an outsider reversible, in the sense that you can actually get back to the original model by back rotating, or whether this is something that is, let's say, too opaque and which would also render these rotated results a little bit useless to the outside world, right?
Yeah, I can definitely ask the others who worked with me on this to see.
Yeah, I would find that.
Yeah, maybe someone didn't tell us and was like, it's great. So
okay, yeah. Okay, thanks.
Yeah. No, this is great. I'm very happy to hear that there's, hopefully some good lines of communication open here. Let me check Zoom again. Okay, so before we break for lunch, I just have some more, much more naive general questions. So first, since I'm not really very familiar with this world, is SFitter open source?
No.
Oh, okay.
No.
Are there any plans to make it open source, or?
I mean, there's no plans right now.
Okay.
I don't know about the future. Like, it's surprisingly difficult to convince certain people to go open source.
I am familiar with this struggle in some areas, so yeah. So I just thought I would ask.
There's no plans for now. I can obviously ask, but I think it's gonna just be swept to the side for now.
Okay. Yeah. It's very, I mean, beyond just use, it's also very interesting to be to try and see how these tools can all connect, and also provides a nice form of communication, or forum for communication. And then I think you might have already mentioned this somewhere in your intro slides, so I apologize if it's like, right there, but for these analyses that you've done using the published statistical models, do you have any papers out on that yet?
No.
Okay, so this is forthcoming work.
Very soon, probably.
Okay, great. All right.
I'm feeling the pressure, let's say it this way, so very soon is the plan.
Okay, well, we don't mean to put any additional
no, not
pressure,
from you.
Yeah, we don't want to put any additional pressure, but we're very much looking forward to this one.
The plan is as soon as possible. Like, we're trying to be done very soon.
Okay, fantastic.
Yes.
Yeah.
So basically, just a nicer way of showing all of this will probably be done.
Very cool.